This is Mr. Z back for another video. I've been on a bit of a hiatus, and I hope you enjoy this one. Here we have a data set of some test scores for a small class. What I'd like you to do is quickly pause the video, type these in your calculator, and just a little bit of a review to make sure that you know how to calculate the one variable statistics and can graph a box plot for the data. So I've already got these entered into my calculator in the list 1. Alright, I don't need to sort them or anything. I hit stat over to calc, and then I'm going to get the one variable stats of list 1. I'm going to hit enter. Of course, X bar will give me my mean, and if I scroll down I can get the median as well. So if I had to calculate the mean and the median, I notice that they are both 80. So we've got the mean is 80 and the median is 80. The question says, what does this tell you? We just took a test on this. You should be able to identify that if the mean and median are close, then the data is roughly symmetric. Sure enough, if I go in and check out a box plot of my data, remember that when I'm making a box plot, I always want to put the outliers on. Or if I have a Casio, turn the outliers on, or do the modified box plot. That way I get my outliers separate. I'm going to zoom down that bad boy, and sure enough, I get a roughly symmetric graph. What does this tell you? The data is symmetric. What do you see? A symmetric distribution, right? Jenny's score is noted in red. That's this one right here. That's my girl Jenny. How did she perform on this test relative to her peers? Well, if I'm looking at the one variable stats, and I see that Jenny got an 86, and I see that the mean and median are both 80s, then I would say she did better than average. But we get into not just the fact that her score is better than average, but how much better than average, right? How far away, how high above average, all right, is her score? And in order to look at that, we need to know how spread out the data is. If the data is more spread out, then 6 points may not be that big of a deal. If the data is really, really close together, then 6 points higher is pretty good. So one thing that I'm going to look at here, and we're going to talk a lot about in this chapter, is the infamous standard deviation, which I'm getting from the calculator as SX. You will see that change a little bit in this chapter, but for right now we're going to use the 6.07. So I'm going to write that down. SX equals 6.07, and I will come back to that later. Okay, so here on our next slide, we can calculate what's called a standardized value, and that will describe relative position in a data set and to tell how many standard deviations above or below the mean an observation is. This is, by no choice of mine, called the Z-score. I wish I could take credit for that. I can't. It's called that all across the world, not just in my class. Anyways, if the mean and standard deviation of a distribution are known, then the Z-score of a particular observation X is this formula right here. Z equals X minus the mean over standard deviation. Now, I'm going to throw some new symbols at you, and I'm going to change, and instead of X or the observation, or we're going to keep that as X. Instead of writing the word mean, I'm going to use the symbol mu, which is what we use to symbolize a population mean. And for standard deviation, I'm going to use sigma, which is a little circle with a hat. You will see this a lot in this chapter. So we get X minus mu over sigma. Now here's a little bit of work with that formula. Jenny's got an 86, and we're going to calculate her Z-score. So we write our formula down. Z equals X minus mu over sigma. She got an 86. The average was an 80 over 6.07. So again, we're figuring out how far above average, and even 6 points isn't enough. That's why we have to factor in the standard deviation. So when we type that in our calculator, we're going to get 0.99, which is pretty close to 1, and it's positive. So she's about 1 standard deviation above the mean. So her z-score is positive 1. She's 1 standard deviation above the mean. Kevin, my man, Big Kev, all right, he scored a 72. Calculate his z-score. Now, 72, we should be going into this understanding, is a little bit below average, if the average was an 80. So I'm going to plug in 72, which was his score, minus the mean score, which is an 80, over that 6.07, which, when I type that into my calculator, making sure I hit enter first, all right? My dear Aunt Sally would not be happy if you didn't hit enter before you divided by. Anyways, you get negative 1.32. And that is negative. So it's negative because Kevin was below average. So the sign of the z-score is very important as far as determining whether we are above or below average. So he's 1.32 standard deviations below the mean. All right, so we've got Jenny that was above average. She had a positive z-score. We had Kevin that was below average. He had a negative z-score. Let's check out my girl Katie. Katie got an 80. Let's calculate her z-score. So we've got my formula, x minus mu over sigma, 80 minus 80 over 6.07, and we get 0. Well, that means that she is average. If she's 0 standard deviations away from the mean, she's average. So you have negative z-scores, which are below average. You have positive z-scores that are above average. And if your z-score is close to 0, that means you're really, really close to the average. Okay, useful applications of z-score. First off, you can use it to compare the two things that have different means and different standard deviations. For example, Jenny's score on 2 different tests. This is also commonly used when comparing like ACT and SAT. You'll see a lot of that in this. You can get your z-score on the ACT, which is a score in the 20s or 30s, and in the ACT you're talking about a much different score, which is hard to compare. So I standardize those values, making them kind of one standard graph using the z-score, and then it makes it a little bit easier to compare. Anyways, Jenny took 2 tests on Friday, that one in statistics where she got an 86, and one in chemistry where she got an 82. And the question is, on which test did she perform better? Of course, initial inspection, you look at it, you see an 86 is higher than 82. Obviously, she did better on the statistics test. Let's look into it a little bit closer. The stats test had a mean of 80 and a standard deviation of 6.07. We already did the math on that. Z sub S, I put the S just because it's the z-score for the stats test, was that 0.99 that we got before. 86 minus 80 over 6.07, that gave us our 0.99. She was 1 standard deviation above. Now let's check out the chem test. Chem test had a mean of 76, so it had a slightly lower average, and the standard deviation is 4. We should know that a standard deviation of 4 is slightly less spread out than 6. This right here. All right? So if we look at it and we calculate her z-score, z sub c, that's going to be her score on the chem test minus the average on the chem test over the standard deviation. And we're going to get 1.5. So if I'm just comparing those two numbers, I've standardized the scores because now I'm not really paying attention to stats or chem. I'm just comparing the z-scores. She did better on the chem test because she got a higher z-score. She's 1.5 standard deviations above the mean, whereas on the stats test she was only about 1 standard deviation above the mean. So on which test did she perform better? Definitely the chem test. Okay, now here we have 3 examples that I would like you to try on your own. Best thing for you to do right now is, these are the examples that I'm going to work through. These will help you in class the next day. Pause the video. Try these on your own. You can write down the problems if you need. And then I'm going to pop up the flow here in a second. So you're pausing, you're working. Now you have unpaused this video and you have probably worked through the problems. So you should have some stuff on your paper that you're about to check what I'm doing. Okay, so I'm going to space these out a little bit so that I can write the answers below them. so that you can see. Maybe. And let's give us a little bit of space to work on this one. Okay. Smashing. All right. Okay. So let's look at the first one. An incoming freshman, again, it's that kind of same idea. They're taking 2 scores. So I'm going to compare her. She. Yeah. All right. So the first one, so the French, Z sub French should be 82 minus 72 over 8, which gives a Z score of 1.25. Z score on the math, 86 minus 68 over 12, 1.5. All right? Boom. 1.5 is a higher Z score. It's more positive, so she did better on the math. Here we have another application of the using the formula, but a little bit of algebra here. The mean score in stats exam was 75. Okay, that's mu. With a standard deviation of 5, that's sigma. Gregor's Z score was -2. Oh, don't have X. How many points did he score? So that's really asking you for X. I remember a while ago saying that we would never solve for X. I was slightly misleading you. This we are actually solving for X, but it is a rare occasion. So if I look at my formula, X minus mu over sigma, I plug in what I know. Same thing as I do in any problem solving. I take what I know, I plug it into a formula. The Z in this case is -2. X is unknown. I know the mean is 75 and the standard deviation is 5. So I'm essentially finding out which score would give me a Z score of -2. A little bit of cross multiplication here. Multiply both sides by 5. I get -10 equals X minus 75. Add 75 to both sides. I get X equals 65. So he must have scored a 65. Okay, now, this final question is good because it gives us a good, how Z scores is not necessarily based on negative or positive sometimes. So it's asking which is more unusual. Well, being far from the mean is unusual. If you're really, really tall, that's unusual. If you're really, really short, that's unusual. So unusual things happen in both the positive and the negative directions. So if I do the first one, January, high temps average 80 or 36, so that's a mu, standard deviation sigma. July, mean high temp mu is 74, standard deviation is sigma. 55 is my X. So on one side, I'm going to take 55 minus 36, so this is in January, 55 minus 36 over 10, and I'm going to get 1.9. On the other side, in July, if it's 55, I'm going to take 55 minus 74, which is the average for July, divided by the standard deviation of 8, and I'm going to get -2.34. Now, you automatically start to associate positive numbers as being better, but in this case, a -2.34 is far more unlikely because it's more negative. All right, the magnitude of the number is bigger. 2.34 is bigger than 1.9. It just so happens to be in the negative direction. So according to this question, we would say that 55 in July is more unlikely than 55 in June. And I believe that that's all I have for you today. I hope that you enjoyed the video, and I will see you all tomorrow.